Well, I want to take a look at a limit. Limit as t approaches 0 from the right, 1 divided by t to the t. If we try to get it by direct substitution, putting in 0 for t, we got 1 divided by 0, which would be undefined. T approaching 0 from the right, you'd be approaching 1 divided by positive number approaching 0, approaching infinity, but then you got an exponent here approaching 0. So, what do you get? Indeterminate form. Well, what we can do to compute this limit here is we can use the fact that e to the log base e of x is going to equal x. And with that, we could write the limit as e limit t approaches 0 from the right of natural log 1 divided by t to the t. And now, natural log, or something raised to a power, you can take this exponent and pull it out in front, so we can get to here, t times the natural log of 1 divided by t. Still in indeterminate form, you got t approaching 0, it's approaching infinity, but of course t in the numerator, so to speak, could be 1 divided by t in the denominator, so we can look at our limit in terms of e to limit, and now we got this divided by this, and what we have as t approaches 0 from the right is numerator and denominator both approaching positive infinity, candidate for L'Hopital's rule. So now we can differentiate the numerator, and derivative of natural log of 1 divided by t is 1 over 1 divided by t, so just t, times the derivative of 1 divided by t. Derivative of t to the negative first would be negative t to the negative second. So applying L'Hopital's rule, you're going to get a t times negative t to the negative second divided by negative t to the negative second. Now that you get this right here. So the limit we're looking for would equal this limit right here. And then we know that if two functions agree at all but at one discrete value for the independent variable, here t, it could be more than one discrete value, but what the point here is that this expression here and just t are equivalent as long as t is not equal to 0. This one's undefined at t equal to 0. This is not. So this limit, if it exists, is going to equal this limit. And of course now we got a limit we can get by direct substitution. Just put in 0 for t, you get 0. So the limit right here is 0. You get e to the 0, which equals 1. So our limit does equal 1. Now you could look at a graphing calculator to try and confirm your answer, like a TI-84 picture here of the graph. As t is approaching 0 from the right, it does look like the graph is 1 divided by t is approaching, raised to the t power, is approaching 1. It's not defined at 0, but that visually looks like the limit from the right. If you tried to come from the left, I mean, function is not well defined from the left. If you tried to put in, say, negative a half for t, you wind up with a square root of a negative number, not define the real number system. So picture here is kind of goofy looking. I asked the TI-84 color emulator to graph the thing, including negative values, just to see what it would do. Now the TI-89, for example, you can look at TI-89, it doesn't seem to worry about t approaching 0 from the right. It just computes that limit immediately to be 1, which is nice and reassuring. Hope everybody stays safe. Have a fun day.